It's going to be kind of an informal thing. So I'm going to talk a little bit, and then I'm going to show you a couple of pictures and talk about, kind of my perspective on science and how it fits into our modern perception of reality, really. So I wanted to open with a scripture, and Psalm 19 says, "The heavens declare the glory of God. The skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they reveal knowledge. They have no speech, they use no words. No sound is heard from them. Yet their voice goes out into all the earth, their words to the ends of the world." And I think there are different levels at which I see this played out. If you go out on a clear autumn night, a crisp night, you can look up at the sky and you see kind of the magnitude of the universe. You see the stars, and you can kind of see things at that level. But I think even if we dig into science, I think we can see the heavens declaring the glory of God. So the first thing I wanted to do is talk about me and where I came from and how I got here. I thought that might be of interest to you. I grew up in rural Virginia, about 60 miles west of Washington, D.C., in the Shenandoah Valley of Virginia. Very beautiful place, but it's farm country. My parents weren't farmers, but my grandfather had grown up as a farmer. Interestingly, I came from a community where there weren't a whole lot. I think of the people who lived on my particular road around me, most of them were farmers or worked at the local factories. There weren't many people who had ever even attended college. Neither of my parents attended college. I graduated from high school. My father was a mechanic. My mother was a homemaker. And so it's kind of an interesting journey for me to get here, teaching at an R1 university. So my mother was very interested in our education, and we didn't have a television in the house until I was about 13 years old, because she wanted us to read books. So my summers were spent going to the library twice a week and just taking every book I could get out of the library and reading all summer long, because we played outside and we read books, and that was a great thing my mother did for me, I think. My grandfather was a pastor, and at most of my childhood, he did not have a church, but he was going around to different churches speaking, right? Doing kind of evangelistic work, and did a lot of work in the community with people who were, struggling with finances and struggling with addictions. He did a lot of work in that area. So my parents sent me to a Christian school. I went to church every Sunday from the time I was probably a week after I was born until, and often on Wednesday nights. So a lot of church, Christian school, and I was a believer from the age of 5 years old. So I spent.
Did you tell us, Franklin, I might have missed, what church, what denomination was it? Was it Baptist?
My grandfather was a charismatic pastor.
Oh, okay.
And I went to a Baptist Christian school. So I had this kind of very interesting background of many, evangelical but different denominations. My family had a singing group, and I would go sing at the local Methodist churches and Baptist churches and different churches in the area. My grandfather would even speak at those churches. In fact, we often went to African Methodist, Episcopal, and Black Baptist churches to sing, and my grandfather spoke at those. So there was a lot of work in the community. My grandfather's retirement project was this small church, kind of in not the best part of town, and it was a church of very ethnically diverse church for that area. That was kind of the thing he did in his 70s and 80s, and so that's kind of the background I came from. So I went to this Christian school, and I graduated a year early from high school. I'd excelled at math and science. I was really interested in math and science. My mother said, "You can't go off to college, you just turned 17. So I went to the local community college on scholarship for 2 years, and then transferred and went off to West Virginia University. And I did a bachelor's in mechanical engineering and a master's degree in mechanical engineering. And my interest in mathematics and science at that point was really revolved around kind of like cars and machinery and things like that. I was very interested in kind of practical engineering. I ended up where I am now. So So after I finished my master's degree, I remember going in to visit my graduate advisor, my master's degree advisor, and I said, "Do you have a PhD project for me?" And he said, "No, you need to go somewhere better than here." And he gave me a list of schools. And so he gave me this list of schools, and on the list was MIT. So Stanford and Berkeley and other places like that. So I didn't immediately apply to go for my PhD. I went and worked. I paid my own way through college, and I wanted to pay off the undergrad student loans. So I worked for 4 years in industry for a company that made boilers, and I designed equipment. I was a practical engineer for 4 years, did that, and then, you know, when the student loans were paid off and I was in a good financial spot, I applied and went to graduate school and ended up at MIT looking for a project. And I knew that I wanted to do something that was more science-based and not so much. I'd done the practical engineering, I enjoyed that, but I really wanted to kind of move more toward some applied science. So I was looking for an applied science project. And so realized nothing about space yet. I was interested in NASA and the space shuttle, but I hadn't really pursued anything related. I didn't do aerospace engineering. I wasn't really interested in that at that point. And so I got to MIT, and I was looking around for a project. You know, like often you'll TA your first term, take some classes, and then you start looking for a research project with a professor to do the PhD on. And I found this guy. He was in the mechanical engineering department, but his PhD was in low temperature physics from MIT, and he was dealing with quantum fluids. And I was just fascinated by this stuff. You know, just like, wow, the cooling is down to near absolute zero. You get all these quantum mechanical effects. It's really interesting science. And so I started working for him and did my PhD. I took a lot of quantum mechanics and statistical mechanics and solid state physics. So a lot of stuff that was very different from designing machines. And so that's kind of where I moved more toward applied science and away from the practical engineering. Nothing about NASA yet. So one of the reasons I wanted to go into to get a PhD was I wanted to be a professor. There had been one professor in my department when I was at West Virginia University who went to my church. He's the only believing professor I knew of in my department. And he was just a big influence. And I had always envisioned that I would get that opportunity someday if I went somewhere, got a PhD, that I could go to a university and have an influence on young people who were, you know, figuring out life and give them advice and actually be an influence for Christ in the academic field. And so that was kind of my goal, is why I went to academia. So I finished up my PhD at MIT. It took 6.5 years. It was this really difficult project, but it worked in the end. Lots of side stories, but for another time. Anyway, so I finished up the PhD, and then I was looking for academic positions, and in 2004, nobody was hiring. It was like, it was just kind of like a hiring freeze in academia. There were no positions open. It was just, so I started looking for jobs, and there were a lot of jobs available. I found out that, you know, the Jet Propulsion Laboratory at Caltech, JPL, was looking for people, and 5 or 6 different places, you know, national labs. And so my family is in Virginia, and I interviewed at JPL, I interviewed at Goddard Space Flight Center in Greenbelt, Maryland, and I decided to go to Greenbelt, Maryland, because I had a newborn and a 2-year-old Daniel. Remember, you know Daniel and Nathaniel who come here. Daniel sang last week at church. He was a 2-year-old at the time. And so I decided that I wanted my children to be near their grandparents for a while. And so that made the decision that I would go to Goddard Space Flight Center in Greenbelt, Maryland. And so I moved there in December 2004, started the job. A day after I defended my thesis, I had a delay in getting my thesis done, and when I showed up at work, my boss, she said, "You could have asked for a month extension and taken some time off," but I didn't know I could. So I showed up, I defended my thesis, flew back, and started work on December 1st, 2004. And I kind of knew beforehand what I would be working on, but they told me about this James Webb Space Telescope thing that I'd be working on and helping out with the thermal issues on the James Webb Space Telescope. So I immediately got thrown right into the middle of it. They were having all these problems, and I think sometimes people don't realize, they think, well, NASA just launched this thing. It's something that's been developed for years, and the technology is very well developed. That's not at all true, because If you're going to put a space telescope out in space, the only way to justify it is it has to do something that the Hubble couldn't do. And so every piece of that thing, I worked on some composite structural work on that for holding the instruments in alignment. That was at the cutting edge of what could be done. We were verifying, as pieces were being built, it was being verified that it would do what it was supposed to. There were these little tiny flaps they're 100 microns by 200 microns. There are couple 100,000 of them. They're in the optical path. When the light comes in, those can be remotely opened and closed from the ground. It's called the near-spec micro shutters. Those little shutters basically can be opened and closed from the ground by running a magnet across and opening them and latching them electrostatically. So you can pick what objects of the sky you want to block out and which ones you want to look at. And so if there's a really bright object, but you want to take a spectrum of something next to it that's very dim, you can close the flap and basically each day they can set what they're looking at. On the ground, graduate students drill holes in aluminum plates and put them in front of the optical path. But they couldn't do that from space, so they had to design this technology. So, just to give you an idea of how cutting edge that was, I sat in a design review. I was the cryogenic expert in a design review for this technology. And I was sitting next to the guy from Philips who had invented the micromirrors. Does anybody remember those ads from years ago for these video projectors and the little girls talking about the magic of the micromirrors? The guy that invented the micromirrors was sitting on the review panel. And when he got up to say his bit, what he said is, I remember when you all came to Philips and asked us to do the micro shutters. And we said no, because the risk was too high. And then the internal team at NASA took it over, designed the micro shutters, and were successful. So this stuff is right on the cutting edge. So when the James Webb launched in, not this December, but the December before, everybody held their breath and they were like, wow, it launched, a success. And all of us that knew the technology included in that spacecraft, one of my former PhD students was on the commissioning team over that next couple of weeks at Goddard, and he was in the control room in Baltimore, and he said they called that the 2 weeks of terror. Because it wasn't the launch that was so dangerous. Would everything deploy? And when they powered up all the systems, would the electronics work? Would the micro shutters work? Would it go to temperature? If the big tennis court size sunshades didn't unfurl, it would be blind because it would be hot and it wouldn't be able to see the distant faint objects. And so, everybody's like, wow. All the people who didn't know what was going on the inside around me said, wow, you must be thrilled it launched. And meanwhile, I remember Isaac saying that to me, and I was like, well, actually, we need a couple more weeks because all the really risky stuff is going to happen in the next couple of weeks. And so, one of my points here is this is at the very limit of what human beings can do. It has the best technology. It's $10 billion. We put out a $10 billion spacecraft, and we launched it out there, and everybody said, wow, we put it out there. How far is the James Webb Space Telescope from Earth? Anybody know?
Yes.
1 million miles. That's about 4 times as far as the moon is. The sun's 93 million miles away. The next galaxy is 25,000 light years away. So, and that's the closest galaxy. So, we put something out there. We've sent probes out further, to the outer planets. But we spent $10 billion putting something out there. Now, it's amazing. It looks out into space. It sees better than anything else ever has. I'll give you some late-breaking data here in a little bit. But it's interesting to think about, just think about those numbers for a minute. That's 1 million miles from Earth. We're not even near the edge of our solar system. It's orbiting around the Earth, following the moon around, basically looking out into deep space. And so we'll just stop there for a minute. So, people often ask me, you worked at Goddard and that space place, and you worked at NASA, you worked on all this interesting technology. How did you end up here in Wisconsin? I was recruiting students last night. I had 2 dinners the last 2 nights, and students would ask, what's your research area? These are potential PhD students coming to Wisconsin, and they're fascinated by the NASA stuff, and they're like, well, why did you leave? And I said, well, I wanted to mentor students, because yes, I was working on interesting things, but I remember I had that goal of being a Christian professor and influencing academia. And I wasn't doing that at Goddard. I was learning a lot. I was getting a skill set that would be useful when I do the research I do now, when I mentor the students I do now, when I teach the classes. I have a lot of examples from NASA I build into my homework sets. So it was very useful time, but the goal was to get here and to really interact with students. And so that's what I did. After 5 years, I left NASA. I started looking for faculty positions. Got an interview here. The interesting thing is I had gone through an interview process, and there were 2 jobs that I didn't get. One was because there was a hiring freeze in the state. They were ready to hire me, and they got a hiring freeze. And I was sitting at my desk, kind of a little bit down about this. And I got a call from one of the guys that's now my colleagues here in Wisconsin. And he said, we're looking for somebody, you know, his phone rang at my desk at NASA. He goes, we're looking for somebody who is in cryogenics, and especially below 1 Kelvin cryogenics. And would you be willing to apply? And I said, sure. And you know, I got off the phone and I knew that was the one. You know, you get off the phone, sometimes God just gives you a little, I'd been through 2 discouragements. And so I got off the phone and I knew, I sent the application in, but I knew at that moment that I was going to end up in Wisconsin. I'd only ever been to Madison once in my life for a scientific conference. And I had never lived in the Midwest. I'm like, I'm going to end up moving to Wisconsin. And sure enough, I did. Here in the middle. And so I have an interesting story related to that. This isn't science related, but so there's a negotiation process that goes on when you're agreed to take up a professor position, and it's not really about the salary, because that's kind of pretty much set. You know, you're going to take a pay cut if you're coming from NASA to go to the academic world. It's just the way it works. But the negotiation is over how much money they're going to give you to build up your lab and how much lab space you get. So I, was advised, you start high, you ask for several $100,000 to set up your lab, and you ask for this much lab space, and then there's a negotiation from there. I sent the information back to them, and they sent me offer letter to sign like within a few days.
Wow.
And so I found out the story later, what happened. And so I think God did this just to say, you're not in control of where you go, I am. Because what I found out when I got here, as the chair of the department said, I called someone in off of vacation on a Friday to write your offer letter because I was worried. On Monday, the state instituted a hiring freeze. So they sent the letter, they mailed the letter on a Friday. On the following Monday, if the letter had not been sent, I would not have had a job offer. So I got this story after I got to Wisconsin. So I thought of that, and I thought, God's just telling me, I'm in control of where you are, you're not in control. You think you're in control of things, you're not really in control of where you are. So another confirmation, I'm here. That first cold winter, I'm like, I'm supposed to be here, even though I'm freezing.
That's a hiring freeze.
Yeah, it's a hiring freeze. And so they did not hire another professor in my department for over 2 years after that.
What era, what year?
That was in 2009. Yeah, it was. Yeah, I got stuck with a house in Virginia I couldn't sell. I had to rent out. It was a tough time. Yeah, the economy had tanked, and so the state was cutting. It was like no more state hires. So that was an aside I didn't plan to get into. So I still work with NASA. 9 of my MS and PhD graduates now work at NASA. 3 of them worked on JWST and kind of helped. They continued some of the work that I did before I left there. So wrapped up, and they were part of the final part of that. So that's kind of how I got to here and kind of what I do. So I don't do astrophysics. I don't do particle physics. But the technologies that I develop are in support of those efforts. So detectors have to be cold. We're working on a project right now with the Deep Underground Neutrino Experiment. And these projects are trying to understand how the world works, is really what you're doing. And so one of my first points I want to get to is science tells us how. It doesn't tell us why. Because sometimes you'll hear a scientist say, well, we're going to look at this so it'll tell us why this is true. And I'm like, that's not true. Science tells you how. And so there's a definition from the Oxford English Dictionary, and it says, this is what science is. It's the systematic study of the structure and behavior of the physical and natural world through observation, experimentation, and testing of theories against evidence obtained. So I'm going to use an example here. I studied mechanical engineering as an undergraduate student, and I learned how to calculate the strength of different objects. And so there's a table there that has 4 legs on it, and I could draw that up in CAD and do a finite element analysis of it, or write some equations for beam theory. And we could put a load in the middle of that table, and I can tell you how much force there'll be on each leg, how much the table will bow down in the middle, at which point it'll break. I can tell you all about that table and how it behaves under different loads, and we can look at the mechanism of how the legs fold up and all that. That'll tell me how the table works, but it doesn't tell me the why of the table, does it? It doesn't tell me why the table was built. It doesn't tell me the motivation for making it. Some human being decided they needed this table for this purpose, and there was some motivation to do that. And science won't tell me the motivation. I can write all the equations out. It tells me the mechanisms. And we know this because the areas of physics I've studied, like quantum mechanics, it tells you the mechanisms, quantum mechanics, of how quantum particles behave. Statistical mechanics, it's the mechanisms. And so all these things, and I think sometimes we as modern human beings get blinded by the fact that we understand a lot of mechanisms, a lot more than we used to. And we think we've mastered things to the point that we can use them. We can figure out how to make tables. We can figure out how to make electronics and iPhones that do amazing things. But I think, lose sight of how little we do know. And the fact that this universe that we have, we've made understand how to utilize it, but we don't really understand why it's here. And that answer doesn't come from scientific investigation. So, I have an educational opinion, I won't call it a theory, and I think that all 2-year-olds are scientists. Have you ever watched a 2-year-old? What do? They pick things up and they drop them on the floor, and they repeatedly do that, right? That's how 1-year-olds and 2-year-olds learn how the world works. They're doing science. I mean, it's in our very being, right? This idea that we're going to explore the world around us. How do we, as human beings, know how gravity works? How do I know, you can take a 10-year-old kid and they can throw a baseball with the accuracy to put it, right over home plate for somebody to hit with a baseball bat. They don't know the differential equations that describe that. They don't go, I got to take the Lagrangian of this and come up with a set of equations and X and Y coordinates and figure out. You can predict that. We can write the equations for it and do all the math. It'd be a couple pages of math. And you can add wind resistance and all this and spin on the ball. It's a complicated problem. But empirically, experimentally, that individual has thrown a baseball repeatedly and repeatedly figured out this is how the world behaves. We count on the fact that the world behaves the same way each time. The fundamental way that the universe works, it's no coincidence that the early scientists, people like Newton, Pascal, came from a Christian belief, because they believed that the world was ordered, that you could predict what was going to happen next because there was a creator behind it, and therefore, the way the baseball behaves is not going to magically change. The gravity isn't up 1 second and down the next. It's predictable. Now, what we find out as we dig deeper into science is that what we think of, we take a limited amount of information and we build up a scientific theory from it. So what works for baseballs, it turns out, isn't really the full story. If you start looking at electrons or subatomic particles, they don't behave like baseballs. And the baseball only behaves that way because it's an amalgamation or a composition of a bunch of other subatomic particles. If you look inside the baseball, it looks like a solid object to us. It's not. It's mostly open space. It's all these particles bound together by electromagnetic forces, and the baseball seems very, but we get an electron microscope out and look at what the baseball's made of. It's made of these particles that are smaller. And then if you start breaking it apart with an atom smasher with a high energy physics experiment, you find that it's made up of not just electrons, protons and neutrons, but the protons and neutrons are made up of things called quarks. You can break these into smaller and smaller pieces. So I think we have to be careful about taking the current state of information that we have and concluding too much from it. And I think that sometimes is what we do as modern human beings. We go, we've made this much progress, therefore in 100 years we're going to solve all these problems. And I think we're overly optimistic sometimes. And so, there's this whole, my brother-in-law's out in Silicon Valley, and there's this whole kind of culture there that, humans can do anything. We're going to conquer it all. A couple hundred years from now, people will live to be 500 years old. I'm kind of like, I don't know about that. I don't know about that, because I think there are limitations. So I have an analogy for, what it's like to do what we've done with the James Webb Space Telescope. We've taken this thing, we've launched it out there, and we're looking at it in space. So if you go to the beach with a young child, that child will maybe wade out into the water. The waves will wash in some seashells. They might see some seaweed come in. And that child will start to form a mental image or have ideas about what's in the ocean. Right? They're like, there's this vast ocean out there, but they start to see. They may think that every animal that lives in the ocean has a seashell that looks spiraled or curled. They may think that. Or they may think it's only that and the fish that people are pulling in when they, the panfish or the flatfish or, the different kinds of fish that people are hooking at the beach and bringing in, or maybe there's some crabs in the ocean. But if they were to, that mental picture they have is not complete. Because we as adults know that there's stuff in the ocean that's far, huge creatures that would swallow them up in a second. Unbelievable creatures that even we don't know about it as adults, deep in the ocean, that we discover every year or two. They find out there are more creatures in the deep ocean we didn't even know. And so, that child sees this stuff wash in, the waves carry in some things. And we encourage that child to discover and play in the sand and learn about the ocean. And they'll come and ask us a question, and what kind of creature lived in the shell, and we'll explain it to them. It's a sea snail, or it's a clam or oyster. And they'll ask questions, and we'll explain what it is. But the knowledge that they have is limited. And I think there's an analogy. When we launched the James Webb Space Telescope with these probes out there, we're just wading out into the ocean, right? We're launching something that's, a million miles from Earth. It's the best we can do. Tens of thousands of engineers and scientists, the best we can do is launch something out a million miles from Earth. We look out into space and we look at the waves coming in. The waves are electromagnetic waves. It's light waves coming from all over. And we see these light waves coming in and they carry information into us. But it's not complete. It's incomplete. We can see only so far. We have figured out how to see back in time now. We can look at stuff that's further away, and then we shift. Instead of looking at it with a visible camera, we look at it with an infrared camera. And that's what James Webb, that's why it's so cold. That's why some parts are at 6 Kelvin, because it wants to look at objects that, if you go out and at night, you can get an infrared camera, a night vision camera, and you can see people moving around, because you don't see the light reflecting off of them like you do in the daylight. What you see is the heat coming off of them. And so that's what we do, because these things are heavily redshifted because they're moving away from us at a high speed. We can basically shift the spectrum over, look at a different wavelength of light. We can then see the peaks, like, oh, that's a hydrogen peak, and map them and see how far it's redshifted, and we know how far away it is from that. And then how long that light took to get to us, which is how far back in time things are. And so we look back in time. So interestingly, just in the last couple of weeks, there's some new images came out of the James Webb Space Telescope. And I worked at NASA on, the principal scientist for the James Webb Space Telescope is John Mather. He won the Nobel Prize in 2006 for his work on COBE. I became good friends with one of the guys who was a junior scientist at the time, another guy named Harvey, who I would have lunch with him all the time. And we would talk about that project and other things. But John Mather came out, I think he made his statement a week or two ago about the data they're seeing that's coming out of the James Webb Space Telescope. So one of the goals of James Webb was to see back farther in time and more clearly than Hubble could see, and back into the 11 to 13 billion range. Okay, that's quite far back there. Interesting thing is, they were expecting to see galaxies that were very early in their development. It was a surprise for them. And nothing, for a scientist, confirming what you believe to be true is nice. Finding there's some surprise in there and things are different than you thought is actually more exciting. Because, and that's kind of what James Webb was. It's a fishing expedition. Basically looking, what are we going to find? We're going to look back in time and we're hoping we're going to find something that's interesting there. It's going to tell us something. And so, I'll read the statement first. It says, new images from NASA's James Webb Space Telescope reveal for the first time galaxies with stellar bars, elongated features of stars stretching from the centers of the galaxies into their outer disks, at a time when the universe was a mere 25% of its present age. The finding of so-called barred galaxies, similar to our own Milky Way, this early in the universe, will require astrophysicists to refine their theories of galaxy evolution. So the theories that existed were not completely correct. And this is what we find in science, is that we're learning as we go. And even our best effort, we're learning, we're reaching out, we spend $10 billion, we do the best we can, and we find out, we theorize something, but it's not exactly correct. And that makes science interesting to me. It's not a failure, it's actually a success. So what I want to do is try to hook up. Wow, this is very short. Man.
That's great.
It's eerie how our career paths are so similar.
It's eerie, huh?
I don't know what input it is. Do you know?
It says laptop HDMI 1.
Computer, go to the second one.
Laptop
Down
HDMI.
1 to 1.
It says, yeah, computer. There we go. Okay. So what they're talking about here is you see this this is the best we can do. This is back 11 to 13 billion years in time. And what they're seeing is this galaxy no longer looks like this. But we can't see what it looks like because the light that's leaving that galaxy now would get here 13 billion years from now.
Right.
Because it's like if I send somebody that can travel at 50 miles an hour from Milwaukee over here, they're not going to get here for an hour, couple hours, right? And so that light travels at a finite speed. It can't get here. But what we're seeing is these arms on it and this spiral thing. They could never see this before. Maybe a little bit, but they just thought it was smudgy with the Hubble. But now they can actually see. You can see the pixelization is much finer now because James Webb is that much better. But what they can see is this has arms like the Milky Way. And they're puzzled by this because they thought it took a lot of time for this to develop. So what does this mean? It might mean that, hey, maybe the age is wrong.
So we're looking at history by looking at that right now.
Absolutely.
That is history.
That's history.
It's not real anymore. I mean, it's
Yeah.
already in the past.
It's already in the past. So when I talked to teenagers at the youth group about, they said, what did you do at NASA? I said, I built time machines. Yeah, I mean, not traveling time machines, but time machines to look back in time. That's what I did. Because the cryogenics area, the low temperature area that I work in, it enables that because you have to go cold in order to see these things back in time. It's not the only reason you go cold. They look at black holes and they use really cold sensors because they want to be able to see the red shift and the blue shift at the edges of for that Hawking radiation that comes up because they can back the rotation rate of the black hole out of that. There's all kinds of things you can do. You can look for exoplanets with these kinds of things.
Is a black hole, Franklin, that black hole draws everything in and not even light will come out, correct? Is that what I'm...
Right, but at the event horizon, they do spit out X-rays. Right where the gravity is just enough that light can escape. As black holes eat mass, essentially it's some object that got massive enough that its gravity is strong enough that anything that goes in cannot get out, even at the speed of light. And so right at the edge of that, where that gravity just gets to that point, it sends out X-rays, Hawking radiation is named after Stephen Hawking. didn't agree with all his philosophies and ideas, but he
Is he
did
the guy
make
in
this
the
discovery.
wheelchair that was real smart, that
Yeah,
passed away
yeah.
now? Okay.
Yeah, he's the guy that said that we no longer had a need for God because we, and I think that's a misunderstanding because I think,
He didn't see all these things, right?
I mean, he understood them, but you know, I don't know. Maybe people become blinded by, you know,
Really, yeah.
yeah, I think we have to, I think when I look out at the universe and I see how vast it is, how complex it is, you can zoom out as far as you want with this technology, and it's just incredibly complex. You can zoom in with your microscope and look at biological processes. It's just incredibly complex. You zoom in even further and you look at the particle physics, and we don't understand why there's matter and not, why matter and antimatter, why is there more matter in the universe than antimatter? There's another project I'm helping on at UW, the Dune project, and it's trying to look at what's that process by which we have more matter in the universe than antimatter.
Yeah, how's that
looking
possible?
looking at neutrinos. There has to be something asymmetric about the fundamental particles that would make them not annihilate each other. And that's an open question. Nobody knows. The universe, there's another one that, 15, 20 years ago was a big one, was we used to think that the universe was expanding and it would slow down and get slower and slower and eventually stop, or it would crunch back on itself. That was the two theories. Turns out the universe is expanding at a faster and faster rate, the so-called dark energy problem. And nobody has a good explanation for that. There's some interesting wild theories that you can never prove, like, oh, there's a black hole when we're only a event horizon of a four-dimensional, black hole when we're three-dimensional. And there's all these wild theories that, but there's no way to prove them. But what we find is as we start digging in, there was a time when everybody thought atoms were the smallest particle, and now we know it's even smaller. And then there are theories about what makes up quarks. Maybe there's string, this superstring theory. But we don't have super colliders big enough to basically break things down and try to see if they're even there. You need super colliders that are bigger than the diameter of the Earth to do that. So my point is that science is a worthwhile endeavor. But I find that it basically confirms my perspective relative to where God is and we are. And when you look at the universe, you look at the vastness, you look at the complexity, it really does make me think of, who is man that you are mindful of this? He is God. There's no doubt about it. And we're small. That's what I need from it. So if you have some questions, I'll be happy to answer questions. You can hit the limits of my knowledge because there are limits. Go ahead.
So you went into string theory just for a tiny bit. I'd love looking into that actual music.
Yeah.
Might be related to the formation and actually the holding together of all things.
Go ahead.
What have you done anything?
I haven't.
in that?
I'm not a string theorist. I haven't
Okay.
looked at that. I'm not even a particle physicist. I'm a low temperature physicist, really.
Right.
Dabbled in astrophysics and now I'm looking a little bit at particle physics with the project I'm working on.
Yeah, I just thought when you do the matter antimatter, if that comes into that equation.
It may. One of the things they're looking at right now is neutrinos when they propagate because of quantum mechanical properties. If you generate neutrinos as electron neutrinos, there are three types. As they move through space, because they propagate in what we call mass eigenstates, they change from being electron neutrinos into something else periodically. So it's an oscillatory thing, and they
Wow.
change. And so from those oscillations, you can back up the differences in masses between the different types of neutrinos. There's no other way to measure it correctly. The masses are so small. And so understanding how they behave and what fraction of them they're going to shoot electrons from the Fermi lab. They're going to shoot 1.7 trillion electrons per second. Multiply that by 3,600 seconds an hour and 24 hours a day. That's how many neutrinos they're going to shoot a day. And when they shoot this through this enormous spectrum, they will see 5 to 10 a day. That's what they're seeing at Fermi lab right now. They're detecting it's right there. because neutrinos are not charged. They have to hit the nucleus of an atom directly. They just go straight through. So right now there are thousands of neutrinos going through my thumbnail every second. They don't interact with me. They don't bother me. They go straight through. They go straight through the Earth. And so they're very hard to detect. And so this is a very hard project, but the goal of it is to basically they're looking for how do these particles behave. But we don't understand them very well unless there's something in them that tells us the mechanisms of this neutrino.
Is that why you're going to South Dakota?
Well, I'm going to CERN in a couple of weeks to help with installation. I'm doing just the cryogenic stuff related to this. I'm not
Yeah.
doing the particle physics, but
I'm just interested. Yeah, because to me, when we look at that and we look at Let There Be, I love tying those two together.
yeah, the idea of let there be light to me is that to me, if you create light, you've created space-time.
Yes.
That to me, that's what that says as a scientist. Is the idea of let there be light means that's the creation of the physical universe.
You bring up this God particle. There is a lab in Switzerland.
I'm going there in a few years.
Yeah,
Is that what you're talking about?
Yeah, so it's the Higgs boson.
Yeah,
It's
Franklin,
not really a
just,
God particle.
just before I go, how do the scientists on Earth control these things at such a distance? Is it radio waves? Or,
Radio waves, yes.
and they can just shoot those waves?
Yeah, so they send a signal, the
Wow.
signals will, they go off, they decrease it to the square of the radius, so, but we communicate with things that are further out than that.
By radio waves?
Right, by radio waves, yes.
Wow, okay, thank
They're
you.
working on laser communications, would be maybe a better way to do it, because it'd be more directed beam, so it wouldn't spread out as you, attenuate as you.
Yeah, thanks, Mark.
Yep.
You talk about the black holes. I'm fascinated, though, all my sci-fis are wormholes. Are they not related at all? Wormholes and black holes are not related?
Not directly, no. So the idea of wormholes are, we haven't observed it. Theoretically, it's possible there are wormholes on the size order of subatomic particles. Particles could go through, but this idea of a grand-sized wormhole that the whole spaceship could go through has not been observed or even theorized.
How far does the wormhole go? From one side of the galaxy to the other? Do you know where one starts and stops, like a subway tree?
You couldn't know, no. There would be no way to know. If there was a wormhole and you went through it, you wouldn't know where you were going to go on the other side. But the idea is like, there's this space. You imagine you take it's a three-dimensional surface, but you imagine if you had a sheet of something that kind of went around like this, say you took a big sheet of paper and you folded it back. If you were walking around on that sheet of paper, you'd have to walk if you want to get over here, you'd have to walk from this point all the way around. But what if there was a hole through from this surface of the paper to the back side of the surface of that other piece of paper there? You could get a shortcut through there. That's the idea of a wormhole. Because the universe is not necessarily flat. It could be, curved around. We can't really see that. It could be, folded back on itself. Is the universe, does it come back around to where you started? Good.
Do you believe there's aliens besides us, and did God create them too?
I don't know. I mean, I don't think God had to tell us everything he was up to.
No, that was my question too. Like when you said there are new planets out there, are there like more than one universe?
Well, one of the things that NASA's looking at, they're looking for exoplanets, and so the older technology, the Hubble could see Jupiter-sized planets around some stars, and the way they would do that is when the planet came around in front of that sun, that star, it would block part of the light, and so they could see the signal get faint. That is not Earth-sized planets don't block enough of the light for that. And so there are other techniques they're looking at. And one of them is they're looking for the light of that star. You look at it, and when that planet comes around, it pulls it toward you. And when it goes to the backside, it pulls it slightly away. And they look at the red and blue shift. Is one technique. So you need very sensitive spectroscopy to see the different light wavelengths. So that's one technique that can be used. But they're getting to the point now they can detect Earth-sized planets. And then they can look, one of the things they can look at is they can look at the light coming off that star, coming through the atmosphere of that planet, and see what the peaks are. Get a spectrum and see, is there water, CO2, maybe able to see whether those things are going to, I guess. certain frequencies of light get blocked by the atmosphere, so they can look for attenuation, decrease in those peaks. Where CO2 blocks certain frequencies of light. So you can see that.
For your goal, since you've come to Madison, is there any story related to that where you've seen what the Lord has done
Yeah.
in
My first PhD student was a Muslim. He's not
Wow.
Christian. So,
Wow.
so that's a story.
Praise God.
Yeah. And then, so what I do at the beginning of the semester, I just did this, is I get up and, I give a couple slides about myself at the beginning of the semester, and then I ask the students, some semesters I do it by note card, and I give them a note card, and I say, put preferred office hours on one side, and on the other side, give me an interesting fact about yourself.
Oh, good.
But that's after I get up and I have slides and I talk about, music here at the church. Candace works in InterVarsity, that's a nice one. And then I say I'm a Christ follower, and that I don't just say that affects all my life. It affects how I teach. And one thing it does, it holds you accountable, right?
Right, yeah.
You can't lose your cool with a student. It's difficult, right? You're going to be. I meet with a group of other Christian professors. There are at least 9 in my department who are believers.
UW, wow.
Out of approximately 50, or maybe more than that. And so I met with 2 other believers the other day, and we were talking about this and the fact that, now we're accountable when we get up and say that. And so there are several other professors who do the same thing when we get up at the beginning of the semester. And I think this is important because I have some stories of some family members who have kind of walked away from their faith. And one of the things they said, all the smart people I knew were not Christians. I told them, colleagues, that I said, even if it's just that, the student says, you know what, there's somebody who's a professor, and they're a great believer. If there's 9 of us doing this every semester in the department, these students that are moving through the department, they're going to see at least one of us in the course. If 1/4 of us are believers, they're just going to see that. They're going to see an introductory class with a professor themselves. The guy who was talking about this was a guy from Crew. He said, don't, say which church you go to. Just say, I'm a Christ follower. I follow Christ. Particular denomination.
Gary, it's all about
Christ.
Well, I was just going to add, I want to say this is a little over my head is quite an understatement.
Almost everything is.
You have the technology to go back in time 1 billion years to see how the universe developed. Is that correct?
Well, NASA has it not to go back in time, but to see back in time. Yes.
Yes, that's
13 billion years.
13 billion years. You can see back in time 13 billion years.
Because you see the light that's getting here now, and it took that long to get here.
My name's Chuck, I was just a kid then.
So I remember my grandfather was a pastor, and I remember I went to work for NASA, and I didn't know how he was going to take this. The universe is very old. And I went to talk to him, and he said, "What are you doing there?" I told him. He said, he used the statement I got. God didn't tell us everything he was up to. That came from my grandfather. And I remember him saying, "Yeah, the universe is very old. God didn't tell us everything he's been up to all this time. What do you think we are?" It's So I didn't know him being an older Christian. I didn't know what his theories were on how old the universe was. But he was like, he's like, yeah, God's not responsible to tell us everything he's been doing.
Okay, so we put.
I don't think he minds us looking at it, but he didn't necessarily tell us everything before.
No, I have also one question. Like, the universe, our universe have a certain time, like, 365 days, 24-hour time period.
Yeah,
when you go further, does it change the, 1 minute in, the space here is like 12 hours?
Right, so, on the Earth, we do have like a 24-hour day. If you went to another planet, you go around. But, if you were in our solar system, the approximate time that would pass during a second would be about the same.
Right.
However, if you go near a black hole, let's say you were to go near a black hole and hang out there for a while, and then come back to us, we would all be older than you. And this is the general relativity. Or if you were to travel at high speed, time passes differently. Speed of light is constant, not time. We think of time as being constant because we live in constant time, essentially. But they've measured this. They put atomic clocks on airplanes and flown them around at a higher speed than other people in the command. When they bring the two atomic clocks back together, way over in multiple decimal places, the times are different. It's been experimentally confirmed. They've taken clocks to the tops of mountains where the gravity's a little less because you're further from the center of the Earth. And the clocks read different. Way over in like the 20th or 30th decimal place. But the time is different. And so we don't, you know, we exist in a world where time marches along, right?
Yeah.
But, you know, I think God exists outside of all this.
Yeah.
In the universe. I think he exists eternally. And I think, you know, we think eternity as being a long time. I think eternity is just a completely different kind of existence.
So if I was to go live at the top of a mountain at a different elevation, would I live longer?
Well, that depends on other factors, right? But the amount of time, so the amount of time to you that would pass. So people are like, well, if I went near the black hole and time passed slower for me, would I notice that? No, it would just seem like a day passed, and 10 days would have passed for somebody else, you know, of time. So I don't know if you'd live longer. It's so small, that effect is, you know, it can only be measured with the most precise atomic clocks. It can't be measured with
You know,
time that you would measure.
no, apart from science and religion, like in India, like Hindu, there is a rishis, like, you know, people like him, they leave all the earthly belongings and go live in the mountain. They say they live longer, but I never, like, you know, seen anyone or like.
That probably has to do with lifestyle. They probably get a lot of exercise. They probably don't eat. They don't live to excess. They probably are healthier. It's probably what it
Family,
is.
nothing.
No stress. No stress, right?
No coffee. Yeah, no coffee.
No kids coming to no college tuition to pay for it.
So my word to derail it is the very end. So when you look at like Ken Ham kind of stuff,
Yeah.
So yeah, it's. I am not a biologist. I don't dig into biology because I'd be stepping in an area that I'm not an expert in. I have a colleague at the university, Jeff Harden, who was a believer as a biologist. He was chair of the biology department for a long time. And you know, he's a very old world. He has a view of that perspective too. From the physics perspective, the universe looks very old.
right?
That's what I say. I think the Earth is old too. I don't. The biology, I don't dig into that. If you're interested in that, I could introduce you to Jeff Harden. I mean, he's written some books. He can certainly point you in the right direction with his books. But yeah, I don't think God plays tricks on us. I don't think he made the universe look old and it's not actually that way. It's what some people's arguments are. And he wouldn't have to put stuff out there that far away to try to make it appear this way to make the world work. So I really believe it is old. Is our number exactly right? Probably not. As we're finding out now from this data, it's probably not exactly right. But the universe is an old thing.
I just wonder if it's a net positive or a net negative to have that younger Earth mindset.
I try not to. Yeah, I try not to get into it with people over that. I think people can have different viewpoints on this, and it has, as believers, and I don't think it has any effect on our eternal fate or how we live our Christian life. You know, whether these galaxies are out here, they don't even have to know they're there to serve God, right? I mean, it's interesting to me, but it doesn't. You know, that's one of the things I struggle with at NASA. Like I'm doing all this work, but it really isn't helping anyone. So I said I want to go to the university because this is interesting stuff, but it's not curing cancer. It's not making people's lives better per se. Indirectly, maybe there's technology that's developed along the way that spins off and makes the world more comfortable and safer for us, for sure. But yeah, I don't want to argue over. I don't want to break fellowship with someone over an issue like this, and have conflict when it doesn't affect our faith necessarily. I think there are people out there who this viewpoint, having this, will young people who I think talking to them will help, because it won't be like, if you believe one thing and then you go into the university and you find out that the thing that you're believing is not possible, it doesn't line up with physical reality. And some people lose their faith as a result of it. So I talk to young people about this kind of stuff.
We're gonna hit that tomorrow, actually. Our theme as a church is it's all about relationships. And the phrase that came to me ever since I came here was from the beginning. And so I'm actually going to Genesis 2 tomorrow, and I'm gonna be showing the first relationship with God with Adam, and just the intimacy of that creation story, but I'm not gonna get into if it happened,
Right.
at this time or at that time, because the whole point of that story is to establish love the Lord your God with all your heart, soul, mind, and strength, and then God bringing the woman to the man, and that this is the first relationship that we have, and this is the story of that, and this is what we're to follow. I'm someone who believes in a real Adam, a real Eve, a real garden, I believe that God, in the realm of his possibility, this could be. And so I'm going to take him for that, because I'm a Hebrew guy.
Right.
And I love the poetry of Genesis 1 into the story of Genesis 2 and 3. I love the way it's put to us by the Lord. And so, yeah.
But the mechanism by which that universe got there,
I'm not going to go into that, because it's not relative to relationships or everything. So I'm happy to hear your testimony of how that worked out. Yeah.
I'm trying to get my head around this 13 billion year thing.
Me too.
How do you know when that light started? In order to have 13 billion years?
Well, so you can measure how fast the universe is expanding.
Okay.
So that's what it's. So, yeah, maybe I should have brought a balloon along with me. So, you can. So, if you take a balloon that's half inflated and you put 3 dots on it, and they're all an inch apart, and then you take the balloon, you blow it up until those dots move apart from one another twice as far. So if I'm on dot 1 here, the dot that's 1 inch away from me will have moved to 2 inches away. The dot that's 2 inches away will have moved to 4 inches away. And so the speed at which that dot that's twice as far away is moving away from you is moving twice as fast. And so if you look at the universe, the things that are further from you are going away at a faster rate. So you can you can look at the light and you can see, because light just isn't a smooth spectrum. The wavelengths have particular peaks in them, like a hydrogen peak or a carbon peak, a carbon dioxide peak. So what you can do is you can say, there are all the peaks that are supposed to be there, but they're shifted over to longer wavelengths. And therefore I can see how far that redshifting is. And so redshifting is like when you hear a car coming toward you blowing the horn, you hear a lot, it goes up in pitch, and then as the car drives away, it goes down in pitch. The same thing happens to light. And so what happens is, based on, and these are estimates, but based on how fast the universe is expanding, which we can measure by looking at objects and then seeing how far they're moving away, and then based on what that redshift is, you can tell how far away that object is. And you know the speed of light, and so you can say approximately how long that light took to get to you. And so if you looked at the same object and you changed the frequencies you're looking at, you would see that object at a different time. Because the light that's arriving here right now is,
You got all that, right? Oh, wait, I got it.
yeah, so I mean, but the light that's getting here from that object now is that fixed distance is going to give you one. Some other object you're going to look at will have a different set of frequencies. If it's closer, it'll be shifted more or less. The light you start with might be something very bright or more red. It'll be a different object. But the key is that the key markers are the fact that there's the spectral lines, and you can benchmark where things are shifted by looking for those key markers in there.
Is it same as like, in the air, like we throw a baseball, like we were measuring how fast it's coming from there to here.
Yeah.
You reverse it, it's the same way you were like measuring backward in time.
Right. If you knew exactly what the speed of the baseball was,
Yeah.
when we know the speed of light, you could back out by how, but there isn't this red shifting thing. That's the key. That spectral shift is the key that lets you back out where it came from. Because the baseball, if you can't see where it came from, you know it arrived at a certain velocity, but you can't really tell whether it left from twice as far away or 3 times as far away. It's that red shifting that tells you what left. So it's like another piece of information.
What is that balloon? Is it like a weather balloon or came from China?
I don't know. I think it was not a weather balloon. But
All right. Want to thank Franklin. Just have a quick prayer. Dear Lord, we